Hey everyone, Mr. Shatter here to present the chain rule. This video is going to focus on using the chain rule to evaluate the derivative of complex functions. And when I say complex functions, I'm talking about functions that have multiple layers. Let's get right in with the definition of the chain rule. So the chain rule is defined to be if f is a differentiable function at the point u equals g of x, and g is differentiable at x, then the composite function f of g of x, which we more commonly write as f of g of x with the parentheses like that, g of x is inside the f, is differentiable, and the derivative of the function is equal to f prime of g of x times g prime of x. Okay? So essentially what you're doing is you're taking the derivative of the outside. So you're doing the derivative of the outside evaluated at the inside. Okay, so evaluated at the inside, and then you times by the derivative of the inside. Okay, so this is what it is. So the chain rule is basically f prime g of x times g prime x for as many layers as you need to go. So you differentiate the outside function, evaluated at the inside function, multiplied by the derivative of the inside function. Because of this, the chain rule is often thought about as the outside-inside rule. In other words, you're differentiating the outside function, evaluated at the inside, and then multiplying it by the derivative of the inside function. So we're working our way outside towards the inside. So start on the outermost layer, and you work down to get to the innermost layer. Okay? Let's try this on an example of f of x equals sine of x squared plus x. So understand, first of all, the layers involved in this question. In this question, you have two layers. The first layer is just simply the sine of x, the sine of any angle. And the second layer is the inside piece, x squared plus x. So specifically, in this problem, sine of x represents our f of x, and x squared plus x represents our g of x. And so we know the chain rule is defined to be f prime evaluated at g of x times g prime x. So let's do it. So the derivative of f is equal to, so we're going to take the derivative of f first. So f is the sine x. So the derivative of sine x is cosine x, right? So it's cosine evaluated at the inner function multiplied, so that's the inner function piece right there, multiplied by the derivative of the inside. Now the derivative of x squared plus x is simply 2x plus 1 in parentheses there. Okay? And that's the function. It doesn't really clean up much more than that. I would probably just take the 2x plus 1 and put it in front of the trig function so it doesn't look like mistakenly it's part of the angle or anything. So that is what the derivative would be. Just move it right up there. So 2x times cosine of x squared plus x. So one thing to consider is how far you have to simplify these functions, these derivatives. So I present Shaq's simplification rules. So don't go crazy here. Let's pump the brakes. You don't need to simplify these things an insane amount. Here are the Shaq simplification rules. Number one, you're not allowed to leave negative exponents in your problem. Okay, so make sure you adjust the problem so it doesn't have any negative exponents. Number two, you're not allowed to have any fractions within fractions. So if you have like a fraction and in the numerator or the denominator, you also have another fraction. You kind of get rid of those. Make sure you multiply by some denominators to get rid of those fractions within fractions. And number three, make sure all of your like terms are combined. So don't leave any x's or x squares uncombined with any like terms. If you follow those rules and you can say yes to all three, then your derivative is probably as simplified as it needs to be. Let's try an example. Find the first derivative of tan squared x. So recall that tan squared x is actually tan x squared, right? So let's consider the layers. The outermost layer of this function is just simply x squared. The outermost layer is something being squared. The innermost layer is tan x. So this represents our f of x, and this represents our g of x. So the derivative f prime x is equal to the derivative of the outer layer. Well, the derivative of the outer layer is just 2 times the inside raised to the first power, right? So 2 times the inside is just tan because the inside is the g. And then you need to multiply by the derivative of the inside. And the derivative of tan x is just simply secant squared x. Okay? And then you can ask yourself, do we have any way we could simplify this? Well, we know that tan is sine over cosine. And we know that secant is 1 over cosine. And so I suppose if you'd like to, you could simplify this to be 2 sine x over cosine cubed x. It's really up to you if you wanted to leave it like that or you wanted to leave it in its initial form with the tans and secants. I tend to like sines and cosines a little bit better. Let's try this one. Find the first derivative of this quotient. Well, there are two things happening here. The first is we're going to definitely have to do a quotient rule, right? Definitely have to do a quotient rule. But the second thing that's happening is when we have to do the quotient rule, this numerator is a layered function. Specifically, it has 2 layers, right? Within the numerator alone, the outermost layer, which we'll call f of x, and I know it's a little confusing because the original function is called f, but the outermost layer is the square root of x, and the innermost layer is 3x squared plus 2x. Okay? So I'm going to need this when I differentiate the numerator. So if I do the chain rule, or the quotient rule, it's going to be f prime x equals low d high, so it's going to be 5 times the derivative of the numerator. And this is when I need to use my chain rule. So the chain rule of this says that I need to take the derivative of the outside layer. Well, the derivative of the outside layer is the derivative of the square root of x. So I'm going to simplify this to x to the 1/2 power. Okay? So the derivative of x to the 1/2 power is 1/2 evaluated at the inside, which is 3x squared plus 2x, raised to the negative 1/2 power, times by the derivative of the inside. This is the chain part of the chain rule. So 3 times 2 is 6x to the first power plus 2. So this whole thing together is low d high minus high d low, which is minus the square root of 3x squared plus 2x times by the derivative of 5, which, ooh, that's nice, that's 0. That's going to wipe this whole term out, which is super great. All divided by 5 squared, which I'm just going to write 25. Okay, so my Shack tips are not satisfied yet because I have a negative exponent here. I also have unsimplified terms. This 5 times the 1/2 and likely times the linear term of 6x plus 2 should probably be simplified. Let's see if we can get it to be a little cleaner. I also have fractions within fractions, which we'll have to get rid of in a minute. So 5/2 is this piece, and then the 3x squared plus 2x raised to the negative 1/2 power. I'm actually just going to put that on the bottom. So it's going to be the square root of 3x squared. Don't know why I wrote a 2. 3x squared plus 2x. And now that's positive because it's raised to the negative 1/2 power. And then the 6x plus 2 I'm going to put on the numerator. And then I also have a 25 on the bottom. So the 25 on the bottom I'm just going to multiply by 2 and make it a 50. I'm just going to make this a 50. And then I can simplify 5 divided by 50, and that's just going to be 1 over 10. And that's as far as I think we could take the problem. If you'd like to get rid of the 1 and then the parentheses will go away, it looks like this is our derivative.